Let us discuss the notion of separated and connected sets. Let's start with the definition. Let's say we have two subsets A and B of a metric space X. And we will say that A and B are separated if the following two things happen. If A intersection with the closure of B is empty, and the closure of A intersection with B is empty. This means that no point of A lies in the closure of B, and no point of B lies in the closure of A. This is separated. And then we will say the opposite of being separated, or separable if you want, is being connected. So a subset of the metric space X is connected if it's not a union of two non-empty separated sets. So here we have our two definitions. So let's see some examples. For instance, let's start with something simple. The set of, well, let's be precise here, the set of points in R such that the absolute value of X is in between 0 and 1. Is it connected or not? So we can sketch it, right? We have -1 here, 1 here, and 0 is out. So it's the union of, we can write it as the union of -1, 0 with 0, 1. Okay. And here we see that it's a union. The two sets we have, 0, 1 and -1, 0, those are clearly separated, okay? Because if this is A and this is B, okay, we have that A intersection closure of B, okay, that would be -1, 0 intersection with closed interval 0, 1, that is empty, and the closure of A intersection with B, that is the closed interval -1, 0 intersection with 0, 1 open, that is also empty. Okay, so according to the definition, A and B are separated, and therefore the original set, let's call it E, is not connected. Okay. Now, more examples. The interval, the closed interval, -1, 1. This one is connected. Okay, but to see that it's connected, we need to show that it's not a union of two separated sets. This makes sense because in any way I try to split it, so let's say I try to split it here, I will be leaving that point out, right? I will create two pieces, but those two pieces will leave one point out. In any case, it's more difficult to show that a set is connected than to show that it is disconnected. We will show that all intervals in the real line are connected. More examples. We could consider the rational numbers, right? The rational numbers are not connected as a set in the real line. Okay, why is so? Well, we can always have the set of the rational numbers, right? And we can always just pick an irrational number. Okay, let's say that we have x that is an irrational number, and we take our two sets that are negative infinity x and b that is x infinity, open intervals. Like this, I can take the intersections of these sets, right, with the rational numbers, and this is going to give me two separated sets. Okay, so this cannot be connected. Just to keep the notation as we had it, we can right away just take the intersection like this and show that A and B are separated. Okay, so with this we show that Q is not connected. In the same way, the rationals are not connected because we could split the rational numbers at any rational number. Okay, and we also have seen the Cantor set. This one is also not connected. The nice thing about connected sets in the real numbers is that they are very easy to characterize. There is this theorem that says that if we have a subset of the real line, it's going to be connected if and only if it is an interval. Okay, what do I mean? That is, if x and y belong to E, then any z that is in between must be in E. Okay, so this is the property that defines being an interval, that given 2 points in E, all the other z that we can find in between those, then those must be in E. Okay, so this is the theorem that we want to prove, and we see that it's an if and only if, so we need to prove the two directions. So let's just start assuming that x and y are in E, and let's pick some z that is in between those. Okay, and let's assume that z does not belong to E. If we do like this, we can write E as AZ union BZ. Okay, what are these AC and BC? Well, AZ is E intersected with negative infinity Z, and BZ is going to be E intersected with Z infinity. Okay, when we do that, these AZ, BZ are non-empty, okay, because X belongs to AZ and Y belongs to BZ, okay? And then, well, they are separated, right? Because AZ is contained in negative infinity Z, and BZ is contained in Z infinity. And these two half lines are separated. So then AZ, BZ separated, okay? Because they are separated, then E is not connected. Okay, so this completes one of the directions, so we need to prove the converse. To prove the converse, suppose now that E is not connected. Okay, and if it is not connected, then there exist two sets A and B separated. And non-empty. Okay, such that A union B equals E. Okay, so now we can pick X in A and Y in B. Okay, so we have our two pieces. And we are going to pick our X in A, Y in B. Well, it may be like this also, okay? We can assume without loss of generality that X is less than Y, okay? Because otherwise we can say Y less than X. So either way, it's going to be the same argument. Okay, and then we are going to define Z, which is the supremum of A intersection with X, Y, okay? So in the picture, the point Z we are talking about would be this one here. Z belongs to the closure of A, okay? In which case, cannot belong to B, which means that X is less or equal than Z less than Y. Okay, and now the two options that I was saying, if Z is not in A, then necessarily X less than Z less than Y, and we are done. And if Z is in A, then what happens? Then C must be not in B, and therefore there must exist Z1 such that Z less than Z1 less than Y, and Z1 is not in B. Okay, then X is less than Z1 less than Y, and Z1 is not in E, and that finishes the proof, because we have been able to find a Z1 that was in between X and Y.